Monumental engineering began with the simplest tools. How did ancient cultures build the pyramids and the Great Wall without modern machinery? The answer has been hiding in plain sight all along. This journey will show you the 24 everyday inventions that made the ancient world possible. We will uncover how a lever could move the earth and why a simple rope and wheel could lift stones to the sky. You will discover the true source of their power, a secret that transforms how you see every ancient wonder. What forgotten tool do you think was most vital to their success? A lone worker faces a stone slab weighing as much as an elephant. His orders are simple: move it. He does not call for more men. Instead, he slides a long, wooden beam beneath the slab's edge and places a single, rounded rock underneath it. Leaning his weight onto the far end of the beam, he pushes down. For a moment, nothing happens. Then, with a groan of shifting weight, the colossal slab pivots on the small rock and lifts from the ground. The impossible has just been accomplished by one person. This is the raw power of the lever and fulcrum. While the Greek thinker Archimedes would later give us the famous boast, "Give me a place to stand, and I shall move the earth," the tool itself was ancient long before him. It was the quarryman's first resort, the secret to prying loose obelisks from their bedrock cradles. But how could something so simple achieve so much? The answer lies in a concept called mechanical advantage. Think of it like using a long crowbar to open a heavy crate. You apply a small push with your hands over a long distance, and the other end of the bar applies a massive force over a tiny distance, just enough to pop the lid. The pivot point, the fulcrum, is the key. By positioning it closer to the massive load, the worker's small force is amplified into earth-moving power. Without this fundamental tool, the first and most critical stones of every pyramid and temple would never have budged. It proved that human ingenuity could outweigh raw muscle, a principle that would unlock even greater engineering marvels to come. That lever may have lifted the stone, but how did they raise it to such impossible heights? Visualize the colossal ramp systems snaking their way up the side of the Great Pyramid at Giza, a temporary highway for millions of limestone blocks. These were not simple mounds of dirt, but feats of engineering in their own right, massive inclined planes built with precision. An inclined plane is essentially a sloping surface, a simple ramp that reduces the force needed to lift a heavy object to a height. While it requires moving the object a much longer distance, it drastically reduces the effort required at any single moment. Picture a team of laborers dragging a 2-ton block up a gentle slope. They are not lifting its full weight straight up, a task far beyond their collective strength. Instead, they are pulling it along a gradual incline, overcoming only a fraction of its crushing mass with each step. Engineers in Egypt and Mesopotamia mastered the use of these earthen and brick ramps, often lubricating them with water or mud to reduce friction even further. This simple innovation transformed the back-breaking work of vertical lifting into the manageable, albeit lengthy, task of horizontal pulling. It was the indispensable tool that made pyramid construction a logistical reality rather than a fantastical dream. This method of trading distance for effort was a cornerstone of ancient logistics, proving that a slow and steady path could lead to monumental heights. But that ramp and lever would be useless without the stone itself, and extracting it required its own special kind of magic. Deep within a granite quarry, a worker makes a series of small holes along a straight line. Into each hole, he taps a dry wooden wedge. Then he soaks them. As the wood greedily absorbs the water, it begins to swell. At first, there is only silence, then a faint creaking. a groan of protest from the stone. The pressure builds relentlessly until, with a sharp crack that echoes through the quarry, the entire granite face splits cleanly along the intended line. This is the power of the wedge, a portable inclined plane that turned water and wood into a force capable of conquering solid rock. The principle is one of focused power. All the force applied to its thick back is concentrated into a single, razor-sharp edge, multiplying human effort into a monumental splitting force. This simple action was the first and most critical step in creating every stone block for every temple, obelisk, and pyramid. It gave builders the power to dictate the shape of the earth itself, harvesting perfectly sized building materials from the living mountain. Without the wedge, the bones of the ancient world would have remained locked in unyielding cliffs, and its greatest monuments would never have risen from the ground. Yet that same wedge, capable of splitting mountains, created a new and equally daunting problem. How do you move a multi-ton block of granite from the quarry to a construction site that could be miles away? The solution was found in a simple act of observation, watching a log roll. At first, workers placed giant stones on sledges and dragged them over a path of lubricated logs. As the sledge moved forward, laborers would constantly run to the back, pick up the last log, and place it at the front, creating a continuous rolling road. This tedious, repetitive process was the direct ancestor of the wheel and axle. By fixing a wooden disc to a central rotating pole, ancient engineers created a device that transformed friction from a formidable enemy into a manageable force. Instead of the immense sliding resistance of a heavy sled, they now dealt with the far gentler rolling resistance of a wheel. This single innovation was the key to moving the colossal stones for monuments like Stonehenge and the towering colossi of Memnon. But the power of the wheel and axle did not stop at transportation. It became the beating heart of new machines. The potter's wheel used it to spin clay into perfectly symmetrical vessels with stunning speed. More critically for builders, the windlass used a wheel and axle to hoist massive buckets of water from deep wells or lift heavy construction materials to great heights. By turning a crank attached to a large wheel, workers could wind a rope around the smaller axle, generating tremendous pulling force. This conversion of circular motion into a powerful linear force made previously impossible tasks achievable with human and animal power. This rotational breakthrough liberated construction, allowing engineers to source special stones and resources from hundreds of miles away. The wheel and axle did not just move objects, it moved entire civilizations forward, paving the way for an era of unprecedented mechanical advantage and logistical freedom. While the wheel and axle mastered circular motion, another device transformed that rotation into a powerful, pushing force. In the sun-scorched fields of Egypt, the survival of entire harvests depended on lifting water from the Nile to the thirsty crops on higher ground. The solution was a marvel of simplicity and genius, the Archimedes screw. Picture a massive wooden tube with a spiraling blade fitted snugly inside. As laborers turned a handle, the bottom end of the screw would dip into the river. With every rotation, the helical blade scooped up a pocket of water, carrying it steadily upward along the spiral path until it poured out the top into an irrigation channel. This was the inclined plane reimagined in 3 dimensions, a ramp coiled around a central core. It did not just move water, it conquered gravity with a gentle, relentless motion. The screw proved so effective that it was soon used to lift not just water, but grain, soil, and even miners from the depths of dark tunnels. Yet the true power of the screw went far beyond simple lifting. Its fundamental principle was the conversion of a worker's easy, turning effort into a massive, linear force. By carving a spiral groove into a wooden dowel, engineers created a portable press. They placed olives or grapes in a sack, turned the screw to press down a wooden plate and watched as immense pressure squeezed out precious oil and wine. This same principle of generating steady, controllable pressure was harnessed in the terrifying war machines of the Roman legions. The ballista, a giant crossbow capable of hurling spears through shields and men, relied on heavy-duty metal screws to twist its rope springs to an almost unbearable tension. A few turns of a crank could store enough energy to launch a projectile hundreds of yards. The screw gave ancient builders a new kind of control over the physical world. It was the key to applying and, more importantly, maintaining immense force, a capability that bonded materials, fed populations, and defended empires. This simple spiral unlocked a dimension of engineering precision that would shape everything from everyday life to the machinery of war. The power of the screw gave builders immense force, but it was the pulley that conquered the vertical dimension. High on a half-finished Roman aqueduct, a team of workers needed to lift a massive stone block to the top of an arch. One man pulled on a rope, and to the astonishment of any onlooker, the colossal weight rose smoothly into the air. The secret was not in his strength, but in the wooden block above him, a grooved wheel that guided the rope. This is a fixed pulley, a device so simple it seems to do very little. It does not make the lift easier, only different. By redirecting the force, it allows a person to pull downward, using their own body weight for assistance, rather than straining to pull a rope upward. This single change made work far safer and more efficient. But the true revolution came when engineers began linking multiple pulleys together. In a compound system, the rope weaves through several wheels, some fixed and others moving with the load. Here, the magic of mechanical advantage truly unfolds. Each additional wheel in the system dramatically reduces the force needed to lift the weight. A system with 3 pulleys might mean a single worker only needs to exert 1/3 of the effort. The trade-off is distance. For every bit of force saved, the rope must be pulled that much farther. It is a direct trade, intelligence for labor. This network of ropes and wheels was the ancient world's crane. It was the technology that allowed small teams to set the capstones on massive dolmens, those mysterious stone tables from prehistory. It enabled the terrifyingly precise raising of Egyptian obelisks, slender needles of stone that had to be pivoted from horizontal to vertical without a single crack. Without the pulley, the multi-storied temples of Greece and the insulae, the apartment blocks of Rome, would have been unimaginable. It effectively multiplied human strength, making a handful of workers as powerful as an entire legion. By turning the brutal fight against gravity into a manageable, systematic process, the pulley didn't just build structures, it built the very skyline of antiquity. That rhythmic tap, tap, tap echoing through the quarry was more than just noise. It was the sound of creation itself. In the hands of a master stonemason, the hammer and chisel became a single precision instrument. The chisel was a wedge refined to a razor's edge, a tool for focusing immense force into a tiny, controlled point. The hammer was a portable source of impact, a way to deliver that force in a series of sharp, deliberate blows. But this was not a brutal assault on the stone. It was a delicate dialogue. The mason had to listen to the rock to understand its hidden grain and its secret faults. A strike with too much force could shatter a work of art in an instant, while too little would make no impression at all. Different chisels were like different words in this conversation. A point chisel was for the rough grammar of the work, knocking off large chunks to find the basic form hiding within the block. Then a claw chisel, with its serrated edge, would scratch away finer layers, creating texture like the woven folds of a stone robe. Finally, the flat chisel would glide across the surface for the finishing touches, smoothing and polishing until the marble seemed to breathe. This intimate process of subtraction, of removing everything that was not the intended figure, gave us the fluted columns of the Parthenon and the dramatic friezes that wrapped around its walls. It was the tool set that transformed anonymous blocks into the faces of gods and the tales of heroes, inscribing a civilization's deepest beliefs directly into the bones of the earth. With the hammer and chisel, humanity learned to argue with stone, and from that argument beauty was born. That same dialogue with stone, the careful chiseling of form from raw block, would mean nothing if the final structure was not perfectly true. The breathtaking verticality of an Egyptian obelisk is no happy accident. It is the result of a tool so simple it seems almost trivial, a weight suspended on a string, known as the Plumb Bob. Influenced by the unerring pull of gravity, the string provides a perfect vertical reference line, a true plumb line against which all else could be measured. Egyptian and Roman builders used this tool incessantly, checking and rechecking every course of stone as a wall rose from the earth. It was the fundamental instrument for establishing alignment, the silent guardian that prevented a tower from developing a fatal lean or a colossal wall from collapsing under its own immense weight. This simple device brought the abstract, invisible concept of down into the practical, visible world. A mason could hold the string against the edge of a freshly laid block and see in an instant if his work was drifting from true. That single, unwavering line guaranteed the stability and aesthetic harmony of everything from the most humble home to the most ambitious pyramid. It embodied an ancient understanding that true greatness, the kind that could stand for millennia, was built on a foundation of relentless precision and unshakable order. A single man could now lift a stone, but to hoist an entire column required a machine that walked. The Roman treadmill crane was a wooden giant and a frame structure that stood as a testament to mechanical synthesis. Between its sturdy legs hung a massive rotating drum, and attached to that drum was a colossal wooden wheel, wide enough for 1 or 2 men to walk inside it, like a human hamster powering a gear of the gods. This was not pure muscle, it was muscle channeled through genius. The worker's simple act of walking created a continuous rotation. That motion was then transferred through a complex set of wooden gears, a clever reduction system that transformed the slow, steady pace of a man's stride into the immense, powerful torque needed to wind a rope onto the central drum. This machine combined the principles of the lever, the wheel and axle, and the pulley into a single, breathtakingly efficient system. The mechanical advantage was staggering, allowing a small team to lift loads that would have required hundreds of laborers pulling on ropes. You can see its legacy in the bustling port of Ostia, where such cranes tirelessly loaded and unloaded grain ships, their rhythmic creaking a constant soundtrack to Roman commerce. But their true impact reshaped city skylines. These cranes made the multi-story insulae, the ancient apartment blocks of Rome, a practical reality. They lifted the heavy stone blocks and massive roof beams for towering temples, enabling construction to reach for the heavens in a way that was previously unimaginable. The frame itself was the silent hero, a structure perfectly engineered to handle the immense stresses and twisting forces, providing a stable backbone for all that power. This machine marked a fundamental shift, a moment when human labor was no longer just about numbers but about amplification. It was the difference between a crowd pushing and a single mind engineering a way to pull. The vertical ascent of civilization was now literally powered by a wheel that men walked within, a perfect marriage of simple motion and monumental ambition. The rhythmic grinding of stone against metal signaled a new era of precision. In the quarries of Egypt, teams of workers would pull a long, copper or bronze blade back and forth across a block of limestone. This was not a saw with sharp teeth as we know it today. Instead, it was a patient, grinding instrument that used a constant stream of sand and water as its true cutting edge. The abrasive quartz particles in the sand did the hard work, slowly and relentlessly scraping away at the stone with every pull. The introduction of these metal saws was a monumental leap away from the blunt force of hammerstones and flint chisels. It moved construction from brutal fracturing to controlled separation. This new level of control was absolutely crucial for the iconic tight-fitting joints of pyramid masonry. The gap between colossal blocks could now be reduced to less than the thickness of a coin, creating a stability that could withstand millennia. The saw effectively transformed stone from a rough, unpredictable mass into a modular, manageable building component. It enabled the creation of perfectly smooth slabs for paving vast temple courtyards, for cladding the inner chambers of tombs, and for crafting the massive lintels that spanned doorways. This tool represented a fundamental shift in the relationship between builder and material. For the first time, rock could be shaped with a predictable, almost geometric precision. The clean, straight cuts of the bronze saw did not just create blocks, they laid the very groundwork for all architectural refinement to come. That same rhythmic tap, tap, tap that shaped stone had a different sound when it met wood, a softer, more resonant knock. In a Phoenician shipyard, a craftsman swings a unique tool, its blade set like a hoe, perpendicular to its handle. This is the adze, the master key for unlocking the potential hidden within a tree. With each controlled, arcing swing, the adze bites into the timber, peeling away long, curling chips. It is a tool of both brute force and delicate artistry, capable of hollowing out an entire log to form the hull of a seafaring vessel, then smoothing the inner surface to a perfect curve. Its design is pure genius, allowing the user to stand over their work and use the full power of their torso and arms, guiding the cut with precision through the swing's momentum. This was the quintessential instrument for shaping the wooden world. While we marvel at the stone facades of ancient temples, their creation relied on a hidden skeleton of wood, all shaped by the adze. It carved the complex mortise and tenon joints that locked massive roof beams together without a single nail. It fashioned the planks for doors and the intricate frameworks for sprawling royal furniture. But its role was even more fundamental. Every lever that moved a stone, every sledge that carried it, and every scaffold that allowed workers to reach dizzying heights was first shaped from a log by this indispensable tool. In Rome, the adze prepared the wooden formwork into which liquid concrete was poured, creating the foundations for aqueducts and the majestic dome of the Parthenon. The adze was the quiet bridge between the raw forest and the polished city, the tool that built the invisible framework upon which all the visible stone glory depended. It proved that before a civilization could build in stone, it first had to master the art of the wood. The quiet rhythm of the adze gave wood its shape, but a new sound heralded a revolution in perfection, the steady, whirring hum of a spinning lathe. In a Roman workshop, a craftsman draws a bow back and forth, its cord wrapped around a wooden cylinder. With each pull, the workpiece spins at a dizzying speed. He rests the edge of a sharp chisel against it, and in an instant, long, perfect curls of wood peel away. The machine does not carve, it reveals a form hidden within the log, a form of perfect symmetry. The lathe transformed the very nature of creation. It was no longer just about shaping a single object with skill, but about reproducing that object with absolute mechanical consistency. A single artisan could now produce dozens of identical table legs, hundreds of uniform tool handles, or a series of perfectly matched balusters for a grand staircase. This was the birth of true rotational symmetry in manufacturing, a concept that hand carving could never hope to match. Why was this so vital for monumental engineering? Consider the complex machines we have already explored. The treadwheel crane with its system of interlocking wooden gears. For such a device to function smoothly, its gears had to mesh with minimal friction, a near impossibility if each tooth was carved by hand with slight variations. The lathe provided the solution, creating components that were not merely similar, but functionally identical. This repeatable precision was the silent bedrock upon which more advanced technology was built. It marked a fundamental shift from unique artistic creation to engineered, standardized production. The spinning lathe did not just create beautiful objects, it planted the seed for an idea that would one day power the modern world, the concept of interchangeable parts. The quiet hum of the lathe revealed perfect forms, but another tool created the holes that connected them all. An artisan holds a small bow, its cord wrapped once around a vertical shaft of wood tipped with a sharp stone or copper point. With a smooth back-and-forth motion, the bow in his hand makes the drill spin at a dizzying speed, biting into a piece of ivory with a high-pitched whir. This is the drill bow, a device that transformed sporadic twisting into a continuous, controlled rotation. Before its invention, a worker would simply roll a drill shaft between their palms, a motion that was slow, uneven, and tiring. The bow changed everything by converting a simple, repetitive sawing motion into rapid, uninterrupted spinning. It focused human effort into a single, penetrating point. This tool was the key to a hidden world of joinery. It bored the precise holes for wooden dowels, those unassuming pins that locked massive stone blocks together or joined hefty timber beams without a single metal nail. Look closely at the finest ancient furniture or the most stable stone door frames, and you will find the legacy of the drill bow, a network of these hidden connections holding everything in perfect alignment. But its power was not limited to construction. The same rhythmic motion could be used for delicate inlay work, setting chips of lapis lazuli or carnelian into wood and stone to create dazzling patterns. And in its most fundamental role, the drill bow was a portable fire starter. By using a softer wood for the drill shaft and a small, notched plank as a base, the relentless friction would generate first smoke, then a glowing ember, giving its user the power to summon flame at will. This simple bow demonstrated that repetitive motion, when cleverly harnessed, could achieve two seemingly opposite goals, the most delicate artistry and the most primal force. It connected the ancient world not just with hidden joints, but with the very spark of creation itself. That steady, whirring bow drill created the holes for 1,000 hidden connections, but the stability of the entire ancient world rested on a far simpler principle, the unwavering nature of a calm surface of water. A Roman engineer stands at the edge of a rugged valley, the planned path of his aqueduct stretching into the distance. His task seems impossible: to ensure the water channel descends at a perfectly gentle, consistent slope for dozens of miles. His most trusted tool is not a complex instrument, but a long, narrow trough filled with water. He knows that no matter how uneven the ground beneath his feet, the surface of the water at one end of the trough will always be exactly level with the surface at the other. This simple fact that water always finds its own level was the secret to taming the most chaotic landscapes. The Romans refined this into a master tool called the chorobates, a wooden bench as long as 20 feet with precise water channels carved along its top. By sighting along the water's surface at each end of this device, an engineer could establish a true horizontal line across vast, rolling terrain. This was far more accurate over long distances than the frame level, which was better suited for checking a single door frame or a short section of wall. The water level was the silent, non-negotiable standard for every piece of imperial infrastructure. It dictated the exact minute gradient of a Roman road. ensuring that carts could roll smoothly and armies could march swiftly. It gave the aqueduct its life, a slope so precise that water would flow for miles under nothing but the pull of gravity, never too fast to erode the channel, never so slow that it would stagnate. Canals that linked rivers and irrigated entire provinces owed their function to this tool. It translated the abstract concept of level from a vague idea into a physical, measurable reality. That calm surface of water in a wooden trough was the true architect of the empire's veins and arteries, a humble guide that brought geometric order to a wild and untamed world. It proved that the greatest power sometimes lies not in forcing nature to obey, but in listening to its most fundamental laws. A single, sharp click echoes from beneath a Roman cart, a sound that measured the world. With every mile traveled along the flawless stone of the Appian Way, a carefully calibrated gear train connected directly to the cart's wheel would complete a cycle and release a pebble into a metal box. This was the genius of the odometer, a mechanical brain counting the steps of an empire. While we have no surviving physical models, the meticulous descriptions left by engineers like Vitruvius and Hero of Alexandria paint a clear picture of its intricate design. The device translated the countless rotations of a cartwheel into a single, standardized unit, the Roman mile. This was not a tool of raw power, but of pure information. Its true value lay in the unseen world of logistics and planning. Before a single stone was laid for a new road or aqueduct, surveyors using these odometer-equipped carts could map the exact distance between 2 points with unprecedented accuracy. They could calculate the precise volume of stone needed for the roadbed, the number of men required for the labor, and the amount of food and water necessary to sustain them for the project's entire duration. This transformed monumental construction from a gamble into a predictable, manageable process. The click of the odometer did not build a wall or lift an arch, but it told the engineers exactly where that wall should go, how long it would take to get the materials there, and what it would cost in resources. In an empire defined by its roads and aqueducts, this simple mechanical counter was the silent strategist, turning the chaotic expanse of territory into a quantified, controlled landscape. It proved that the foundation of any great physical achievement is not just muscle or material, but perfect, reliable information. Along the sun-baked banks of the Nile, a rhythmic motion defined the day, a long pole dipping and rising like a patient heron. This was the Shaduf, the world's first irrigation crane. Its design was a masterpiece of efficiency, a wooden beam balanced on an upright support. On one end hung a leather bucket, on the other, a heavy counterweight of mud and stone. A farmer would pull down the empty bucket, dunking it into the river. Then, with a gentle push, the counterweight would do most of the work, effortlessly lifting the heavy, water-filled container high enough to swing and pour its contents into a waiting canal. This was not just farming, it was applied physics. The Shaduf took the principle of the lever and made it a part of the daily landscape, a constant, swinging reminder that human ingenuity could lighten the heaviest of loads. While it seems like a humble farm tool, its impact resonated far beyond the fields. By making irrigation massively more efficient, a single family could water a much larger plot of land. This simple device effectively multiplied the agricultural output of the entire Nile Valley. It sustained the dense populations of workers who labored on the great construction projects, freeing countless hands from the back-breaking, all-day task of hauling water by hand. Those hands could then quarry stone, drag sledges, and raise monuments. The Shaduf did not lift a single block for the pyramids, but it fed every single person who did. This elegant tool proves that the foundation of civilization's greatest wonders was not just stone and mortar, but a full stomach, made possible by a simple, swinging pole. A colossal statue of a pharaoh glides across the desert as if by magic, its stone weight borne on a simple wooden platform. This was the sledge, the heavy-duty hauler of the ancient world, and it relied on a clever trick of physics. Unlike a wheeled cart which could splinter under the immense stress, the sledge distributed the crushing weight of a multi-ton block evenly across its broad, flat base. This prevented the stone from sinking into the soft sands of Egypt or the muddy soils of Mesopotamia. But the true genius was in the lubrication. Tomb paintings show workers diligently pouring water, or sometimes even precious milk, directly onto the path ahead of the wooden runners. This was not a ceremonial offering, it was practical engineering. The liquid mixed with the soil to create a slick, muddy paste that dramatically reduced friction, transforming a bone-jarring drag into a manageable slide. Think of it like trying to push a heavy box across a rough carpet versus pushing it across a wet, slippery floor. That simple layer of mud could cut the pulling force required by half or more. This method was the indispensable link between the quarry and the river, the first crucial step in a stone's long journey toward immortality. It demonstrated that sometimes the most powerful solution is not to reinvent the wheel, but to master the art of the slide. A Roman bricklayer taps a new brick into place, then raises two simple tools that hold the entire empire together. In one hand, a wooden triangle, the mason's square, its two arms locked in a perfect, unyielding 90-degree angle. He fits it into the corner of his growing wall. Any gap of light between the tool and the stones reveals an error that must be corrected before another block is laid. In his other hand, he holds on a frame level, a device like a small wooden stool with a plumb line dangling from its peak. He places it on a newly laid lintel stone. If the bob string hangs exactly over the center mark carved on the crossbar, he knows the surface is flawlessly level. This daily ritual was the silent guardian of ancient engineering. The square ensured that every corner was a true right angle, a fundamental rule for structural stability. Without it, the precise interlocking of stone blocks would fail, walls would lean and buckle, and the magnificent rectangular temples and basilicas would be impossible. The square was the physical embodiment of geometric truth, a rule made from wood that translated the abstract principles of Euclidean geometry into a reality you could hold in your hands. Meanwhile, the frame level guaranteed that surfaces were perfectly horizontal. Floors would not slope, doorways would not twist, and massive roof beams would rest evenly, distributing their colossal weight without creating dangerous points of stress. These two tools worked in a constant, silent dialogue. The square checked the vertical plane, the level checked the horizontal plane, and together they imposed a rigid, reliable order onto the unpredictable chaos of the natural world. This was not just about building something that would stand, but about building something that would stand straight and true for thousands of years. The confidence these tools provided is visible in every surviving Roman road, every soaring aqueduct arch, and every meticulously planned city grid. They were the unsung heroes of every project, the daily check that turned ambitious designs into enduring monuments. This relentless pursuit of perpendicular and level was not just a technical standard. It was the very expression of an empire's unwavering belief in its own permanence. The relentless breath of the Bellows transformed rock into refined metal, the very substance of advanced engineering. Deep within a smoky workshop, a smith's hands worked a pair of leather bags, rhythmically compressing them to force a stream of air into a heap of glowing charcoal. With each controlled blast, the embers flared a brilliant orange, their heat intensifying until the very rocks within the fire began to weep shimmering liquid metal. This simple air pump was the heart of a technological revolution. Before the bellows, fires were too weak and unpredictable to reliably smelt the toughest ores. But with its ability to deliver a continuous, controllable draft, the bellows could supercharge a fire, pushing temperatures to a point where copper and tin would willingly separate from their stony prisons and fuse into the alloy we call bronze. This was not just a hotter fire, it was a tamed one, a tool as precise as any chisel. The result was a new generation of tools that were nothing short of miraculous. Bronze chisels held a sharp edge far longer than flint, allowing masons to work faster and with greater detail. Bronze saws, with their sturdy, toothed blades, could cut wood and soft stone with a speed that was previously unimaginable. The bronze axe cleared forests for new cities, and the bronze nail, a humble spike of metal, became the unsung hero that held everything together, from ship hulls to roof frames. For the first time, humanity had materials that were not just found but forged. The bellows did not build a single temple, but it forged every tool that did, empowering an entire civilization of workers with instruments of unprecedented strength and durability. It was the quiet, pumping lung that gave breath to the Bronze Age, enabling the leap from monumental stonework to the intricate metal-reinforced structures that would soon follow. A single wooden frame could produce an entire city. In the vast brickfields of Mesopotamia and the Roman Empire, workers repeated a simple, rhythmic process, pressing wet clay into standardized molds to create thousands of identical blocks. After drying in the sun and firing in massive kilns, these bricks emerged as perfect, interchangeable units. This was not just pottery on a grand scale, it was the birth of mass production in construction. The mold imposed a geometric order onto the chaotic plasticity of clay, ensuring that every single building block was the exact same size and shape. For the bricklayer, this standardization was a gift of speed and strength. He no longer had to spend precious time chiseling and adjusting each stone for a custom fit. Every brick he picked up would lock perfectly into place beside its neighbor, allowing walls to rise with stunning rapidity and creating structures of immense, uniform stability. The true power of the mold, however, extended far beyond humble mud bricks. The same principle was used to cast the bronze gears for complex machines, the iron blades for stronger tools, and the decorative terracotta plaques that adorned countless buildings. In Rome, wooden molds became the temporary skeletons for some of history's most enduring structures. Workers would build elaborate wooden formwork in the shape of an arch or a vault, then pour liquid concrete into the cavity. Once the concrete cured, the wooden mold was removed, revealing a perfectly formed, monolithic structure that carried the weight of an empire. This concept of the repeatable pattern was a profound mental shift. It moved civilization away from the world of the unique, hand-fitted artifact and into the age of the modular component. It allowed for a radical division of labor, where one team could specialize in manufacturing perfect bricks all day long, while another team, miles away, could assemble them into a fortress or an aqueduct with the confident expectation that every piece would fit. The mold was the silent, uncelebrated architect of urban sprawl, the tool that transformed raw, formless material into the countless identical units that built the very fabric of the ancient world. Every grand structure begins not with a stone but with a line. An ancient Greek architect sits with a wax tablet, a pair of bronze dividers in one hand, and a simple, unmarked strip of wood in the other. With a straight edge, he scores a flawlessly straight line. With a compass, he pivots on a single point to inscribe a perfect, unbroken circle. This was not mere drawing, it was the act of giving physical form to mathematical truth. These two tools, the compass and straight edge, were the fundamental instruments for drafting the very blueprints of civilization. They were the bridge that carried an idea from the abstract realm of geometry into the tangible world of stone and mortar. With them, an engineer could plan the exact proportions of a Doric temple, ensuring every column and every space between them adhered to a sacred ratio. He could design the vast, sweeping curve of a Roman amphitheater, a form that could carry a whisper from the stage to the highest seat. He could lay out the grid of an entire new city, its streets intersecting at perfect right angles, imposing human order upon the chaos of the landscape. This practice was rooted in a profound belief that the universe itself was built upon geometric principles, and that by mirroring these perfect forms in their architecture, they were creating a reflection of cosmic harmony on Earth. The famous golden ratio, a proportion celebrated for its innate beauty, was not just a mathematical curiosity. It was a practical design tool explored and applied with these simple instruments. The compass and straightedge were the shared language of the philosopher and the builder. The clean arcs and precise lines they produced were the first whispers of the Parthenon's majesty and the Colosseum's grandeur. They proved beyond any doubt that the most enduring monuments are always born from a foundation of perfect thought. That same spiral principle that powered massive presses and war machines found its ultimate expression in a tool small enough to fit in a plumber's hand. Inside a Roman workshop, a craftsman prepares to join two sections of lead pipe. He takes a hardened metal rod, its surface carved with sharp, spiraling grooves, and carefully screws it into the end of one pipe. With each turn, the tool, known as a tap, cuts a perfect spiraling channel into the soft metal, creating an internal thread. He then takes its partner, a threaded ring called a die, and rotates it onto the end of the second pipe, carving a matching external spiral. When he brings the two pipes together and twists, they lock into a single, seamless unit. This was the die and tap, the duo that mastered the art of the miniature screw thread. This was not about generating immense force, but about achieving perfect, leak-proof connection. The invention of standardized screw threads was a quiet revolution in precision. It meant that any pipe made to the same specification could be screwed into any other, creating a modular network of water channels that could be assembled, disassembled, and repaired with ease. This principle of interchangeable, threaded parts extended far beyond plumbing. It was used to assemble the complex metal components of wine and olive presses, ensuring they could withstand immense internal pressure without bursting at the seams. Early scientific instruments, like the delicate astrolabes used for navigation, relied on tiny, precision-cut screws for their fine adjustments. This technology transformed the screw from a simple machine for applying force into a tool for building complex, interconnected systems. It was the key to creating reliable, pressurized conduits, the very arteries that carried water for the public baths and fountains that defined Roman urban life. With a die and tap, the powerful spiral of the screw was miniaturized and replicated, threading together the very components of a sophisticated society and proving that the smallest details could hold the greatest civilizations together. A merchant's hands hover over a simple wooden beam suspended by a single cord. On one side, he places a stone weight, on the other, a pile of raw copper. He watches his entire trade resting on the moment the two sides hang in perfect, motionless equilibrium. This is the balance scale, a tool that transformed guesswork into guaranteed fairness. Its principle was the lever in its most elegant form, a symmetrical beam with the fulcrum perfectly centered, creating a state of pure balance. But its impact reached far beyond the marketplace. On a Roman construction site, a different kind of transaction was taking place. A foreman carefully weighed portions of slaked lime, sand, and the mysterious volcanic ash that gave Roman concrete its legendary strength. The integrity of an entire aqueduct arch depended on this exact mixture. Too little lime, and the mortar would never set with the required rock-like hardness. Too much, and it would become brittle and crack under stress. The balanced scale brought a scientific rigor to this alchemical process, ensuring that every batch of concrete, every mix of metal for bronze tools, was consistent and reliable. This was the ancient world's most fundamental form of quality control. It replaced the vagaries of a handful or a basketful with the unerring truth of a balanced beam. That simple act of achieving perfect balance did more than facilitate trade. It built trust into the very mortar between the stones. It guaranteed that a wall would not crumble and a tool would not fail, proving that the longevity of an empire was not just about massive stones, but about the meticulous measurement of the materials that bound them together. The final piece of the great Roman puzzle was held in a single worker's hand. High on the scaffolding of an aqueduct arch, a laborer dips his flat, hand-held trowel into a bucket of wet, gray mixture. With a fluid, practiced motion, he spreads the revolutionary substance known as Roman concrete into its wooden formwork, smoothing its surface with the blade's edge. This simple tool, a modest metal blade fixed to a handle, was the master key that unlocked the potential of the ancient world's most versatile building material. Before concrete, the trowel was the essential partner to the bricklayer and stonemason, the instrument that placed the mortar which bonded individual units into a cohesive, load-bearing wall. It ensured that the glue of civilization was applied with just the right thickness and consistency to create a bond stronger than the materials it joined. But with the advent of concrete, the trowel's role exploded in importance. This was no longer just about joining bricks, it was about sculpting liquid stone. The trowel became the primary tool for placing, spreading, compacting, and finishing this pourable rock. It allowed workers to fill the most complex wooden molds, creating structures that were not assembled but born whole. Think of the immense, seamless dome of the Parthenon, a masterpiece that required not a single supporting pillar. Its existence relied on teams of workers with trowels, meticulously layering the concrete into a perfect, monolithic shell that seemed to defy gravity. Or consider the vast, soaring vaults of the Roman baths, curved ceilings that would have been impossible to build from individual stone blocks. In these spaces, the trowel's sweep left a smooth, continuous surface that was both structurally sound and breathtakingly beautiful. This humble tool represented the ultimate fusion of human skill and material science. It was the final, intimate touch in the grand process of construction, the gesture that transformed a pile of raw, granular components into a single, unified, and enduring whole. The legacy of the trowel is written not in individual stones, but in the seamless, poured strength that still stands as the backbone of the ancient world.